Hello and welcome. Design of experiments, or DOE, is a powerful form of applied statistics that we can use to analyze and optimize our processes. Specifically, DOE is a framework for planning and conducting experiments to study the effects of multiple input variables, or factors, on an output variable, or a response. We typically use DOE during the analyze and improve phases of the Six Sigma DMAIC approach. In the analyze phase, the team uses DOE to study the critical inputs to identify the root causes of the problem in focus for the project. DOE helps to systematically explore the relationships between various process inputs, or X's, and the output or response variable, or Y. This allows us to determine which critical factors have a significant impact on the process performance and prioritize them for further investigation. In the improve phase, the team focuses on optimizing these critical factors to achieve the desired outcomes. We can use DOE to systematically explore different combinations of factors and levels to identify the optimal settings that maximize the desired response or minimize variation. This helps us to ensure that the process improvements we make are based on data-driven insights and will lead to sustainable results. We can categorize DOEs into 5 types. First, full factorial DOEs help us test factors across all possible combinations in order to determine which factors are statistically significant. These DOEs are sometimes referred to as characterization studies. Because full factorial DOEs test every possible combination of factor settings, the number of experiments grows exponentially with the number of factors. This increases the time and cost and can make it impractical when we have a large number of factors. This brings us to the second type, which is the fractional factorial DOE. As the name suggests, fractional designs reduce the number of experiments needed by selecting a fraction of the total possible combinations of factor levels. We use this approach to estimate the main effects and low-order interactions with fewer experiments, making it more practical for studying systems with a large number of factors. However, there are trade-offs we must be aware of when running a reduced number of experiments with fewer factors, such as confounding higher-order interactions with main effects and lower-order interactions. Fractional factorial designs are often used as screening designs due to their ability to efficiently identify important factors, serving as a starting point for more in-depth experimentation and optimization. This is our third type of DOE. Screening DOEs are used in the early stages of experimentation to narrow down and identify the most important ones from a large number of potential factors. The goal is to screen out the factors that have little or no effect on the response variable, focusing future experiments on the factors that significantly impact the response. In other words, if we were working with 5 factors, we could use a screening DOE to help us determine which of the 5 seems to be the most significant. These designs often employ fractional factorial setups to manage the experiment's scope and complexity. The fourth type is the optimization DOE. These help us identify optimal factor settings in order to hit specific targets. Screening designs are efficient for identifying significant factors from a large set by testing the most factors with fewer experiments, focusing on breadth rather than depth. In contrast, optimization designs involve fewer factors but are designed to deeply explore these factors' effects and interactions, providing a robust framework for understanding and achieving optimal conditions. Optimization designs are often a series of experiments focused on modeling the relationship between the response and key factors to optimize the response. The fifth type of designed experiment is the Taguchi method. This approach focuses on robustness and the quality of the output. Taguchi methods use orthogonal arrays to study a large number of variables with a relatively small number of experiments and emphasize minimizing variation in the process. Each type of DOE has its own strengths and is suitable for different purposes. The choice of which DOE to use depends on factors such as the specific objective of our experiment, the number of factors being studied, the desired level of precision, sample size, and statistical power, the complexity of interactions, and the sequential nature of the experiments. We may be required to use a specific DOE approach based on regulatory and compliance requirements in some industries. And of course, we must consider resource constraints when selecting an appropriate experimental design. That wraps up our review of Design of Experiments, or DOE. We'll see you soon.